to understand file system. So we discussed, disk layout where data access blocks and inode table and inode bitmap and superblock. Okay, and on top of that, we have different allocation strategies, right? So contiguous allocation, linked allocation, and FAT allocation, and finally it goes to index allocation, which is most common, most popular design in file system, where there's specific index blocks pointing to location of file. So let's say your file system, your file is divided by 4 kilobyte chunk. So 4 kilobyte, which is same as block size. Okay, which is block size, 4 kilobyte. Okay, so the first block pointing to this physical block location. If you access within this first 4 kilobyte chunk, then the contents are stored in the block number 9. If you access second file system, second block chunk here in the file, this is file, right? Then this index block say the corresponding data blocks are located in block number 16. Okay, so this index block are stored in the directory in the example, but there are some kind of the implementation. But this illustration saying that by leaving a directory, you know the index block. After reading an index block, you can locate actual data blocks by looking at this index block. So it's good. So index blocks, works well for, supporting the random access. On the other hand, FAT and linked allocation, random access performance is really poor for random access. However, the downside of this index allocation is you need extra index block in every file. So in index block, we can treat index block as a metadata, which require large space over wasting space for unneeded pointer. Unneeded pointer is this one. So especially when file size are small. So if you can create a 4 kilobyte 1 byte file, then you need 4 kilobyte index block, okay, which causes this waste of space. Considering that earlier days, hard disk today are cheap, but when the file system is first invented, hard disk is super expensive. So this wasting space is prohibited cost. So they providing, the file system designer improving this problem by modifying the index structure. What was the idea? Recall that the last time we stopped there, right? What is the idea to reducing the index block overhead, especially when the file size is small? Can anybody remember? Multi-level is one thing, but I'm specifically asked when file sizes are small. When file size is small, then what's the idea? Embedding index block to where? Embedding, not all the, okay, I know. Okay, so here, these inode, 128 byte inode, within inode, this is undescribed inode, right? 128 bytes, or in inode, there is some array which is called direct blocks, typically 12. So each block, data block is 4 kilobyte. So this is number 12. So if file size is less than 48 kilobyte, then these direct blocks are used for locating data location. So let's say here is a file, and if file size is 48 kilobyte, and this 4 kilobyte chunk is indexed by direct block, which is embedded in inode. So by reading inode, you know the location up to 48 kilobyte. However, we cannot make inode index infinitely large. It's like the same reason, right? So when you create a file, you need to create index file. You need to create inode. So if you can create 1 byte file, and then you have to create 128 byte index, inode has to be written. So if it's really large, then space over is wasted. So 128 byte is norm standard metadata size. Okay, so that leads to limited capacity for using the direct blocks. More than that, if file size is bigger than 48 kilobyte, then using the level of indirection, the another multi-level indexing structure, where single indirect block is pointing to location of index block. An index block likewise having a pointers to print. Double indirect block is 2 level. So where the pointing to the second level index block, the second level index block is pointer pointing to next level index block, and the final index block pointing to data locations. Okay, that leads to this kind of computation. So each inode has 12 direct pointer and 1 single indirect pointer, let's say. Then block 4 kilobyte disk address having this number pointer for 4 kilobyte block. Okay, so let's say what is the maximum file size according to this index scheme, where 12, okay, and single indirect block, this is 4 kilobyte, and each entry has 4 byte pointer, right? So this number pointer and this is total number of file we can point to. Okay, so when you are creating a file, so up to 48 kilobyte, you use the direct pointer. And more than that, then we can go to indirect pointers, and then the first block here is block pointing to here. And the second block here is block pointing to this one, etc. Okay. So this is kind of working well in general file system, because when you are looking at the file system, in terms of number of files, small files, large files, which one has more, in terms of number, small files and large files, which one is dominant in file system? Small files, much larger number system. So effectively, this scheme, whether you can embedding this index inode, the index block into inode, effectively working for many small files. So good, kind of engineer. So the design is kind of backed by some kind of practice, and file system, file size distribution, and file system designer looking at this distribution and make sense. Decided this design makes sense. All right, so that is multi-level indexing. So likewise, you can compute what is the maximum file size when inode start using the double indirect block, triple indirect block computing. So I can leave it up. The computation of the maximum number of the maximum size of file, I will leave it up to you. Please do it. Right, so that was the multi-level indexing. The other one is a popular extent-based allocation. So this extent-based allocation is kind of used in real today, even today file system using this scheme. So which are kind of replacement for this multi-level indexing. The two popular schemes, multi-level indexing is also very popular, and this extent-based allocation is popular. So if you want to design a file system, those two are basic, most popular way for indexing the directory block. But let's take a look at what's the extent. So allocate multiple contiguous region. We call it extent profile. So in index block, each entry only pointing up to 4 kilobytes. However, if you look at the storage, there are some cases where file system having large contiguous block, say 16 kilobyte block, is pointing. So to locate 16 kilobyte, you need to create 4 entries for indexing. Why don't you using the one single entry that pointing to contiguous 16 kilobyte? That is the starting point of indexing, using indexing the extent. So extent leaf node has what? Starting number and what? Size. Okay. So starting block address and size. So one extent can pointing to large number of directory block when they are contiguous. Okay, so like multi-level indexing, this is the ext4 inode, which has embedded data structure. So this structure has pointing to the first level index. So multi-level indexing using this B tree, like a B tree like structure. So if you can access given, then these are B tree, B plus tree, which searching the index to locate leaf node. So if you're not familiar with how does the B tree organize? How is the B tree organized? Please take a look at the internet. B tree has some kind of range searching. So if you can have some key, and then you can B tree actually finding node to locate the leaf node that pointing to this key. So there's some kind of way to searching comparing to ranges. So take a look at how is the B tree organized. Okay, so eventually locating the final extent, that extent pointing data blocks. Again, these data blocks can be contiguous. So if there's some kind of another block located, extent and list take 4 kilobyte time. So comparing to other index which pointing to 4 kilobyte, nothing to lose. So if you have blocks contiguous, then extent pointing to extent to effectively reduce number of the blocks for indexing. But if only can pointing 4 kilobyte, extending pointing for 4 kilobytes, so nothing to lose. But at the cost of complex implementation of this B-tree index, so they are popular. Okay, so it's when the file system is not fragmented, if blocks can be allocated contiguous, this extent-based allocation, extent-based indexing effectively reduce the size of index because using this contiguity in the physical space. Okay, and providing really good sequential performance. So comparing to the indexed allocation, why does extent-based allocation providing good sequential performance? Why do you think? Why? Multiple blocks allocate place contiguously. Let's say same thing. Let's say extent allocation, they blocks allocate contiguously. Extent and then index block same. So block allocation of blocks are same. Say in index node, blocks allocate contiguously. Extent-based allocation blocks allocate contiguously. But even that, extent-based allocation is faster. Why? Okay, so Minchal actually pointing out the answer. The number of access to disk is smaller. Why? Which point? Why the number of access to disk is smaller in extent-based allocation? Let's say this is disk, and let's say you want to read 16 blocks, and they are contiguously allocated. Okay, yes. For indexed allocation, how many index you have such? 16 index. So index, find location. Index such, find location. Index such, find location. You have to do that. But in case of extent, what? One extent pointing to here to here. So reading one, you can sequentially do it. So this individual index search operation is eliminated. So in case it's providing much better sequential access performance. Make sense? So reducing the number of index search. That's number of index lookups. Okay, so providing much better performance for sequential access in the same compared to index allocation. Okay, that's the point. Good. Good. So, which are kind of common reason that this in extent-based allocation is popular in modern file system. Okay, so the size of metadata is sometimes a bit bigger, but let's not get bothered. So metadata overhead is also very small and good sequential performance. Mostly this is the main reason that the extent-based allocation is popular today. Right, that is all about index. So what do you talk about? We talk about on-disk layout and how to allocate data blocks. So some layout. And here a file. And there's some kind of level of indirection mapping. Okay, how to give in file 4 kilobyte block offset to 4 kilobyte blocks, how to map it. So contiguous allocation, FAT-based allocation, index allocation, extent-based allocation. We learn several techniques. One question. So we look at several different allocation and mapping, level of indirection techniques. And this index allocation and this index allocation, for building this index and searching the index operation, hardware does it, software does it. This searching, so I want to find the file offset, say file offset, 100, then finding location to extend block. So they are put into DRAM. Does hardware traverse it and software traverse it? Hardware does it, software does it. Software. Who? File system. Okay. Then recall that in virtual memory, virtual address and physical address, translation, page table, this one, hardware, right? But in file system, this file offset to physical block mapping and managing mapping, translation, translate this, traverse this mapping done by software, particularly file system. Why this implementation? Why this index implementation, index traversal is done by software? Why does it? Why? Unlike memory system, this translation done by software. What do you think? Any reason? There's mapping, yeah. That's consequence, Minjun. That's consequently, if this mapping is only supported by hardware, then only one type of mapping is page table. But now, this implementation is made by software. There are tons of different indexing schemes are, generated today. But that's consequence because, indexing is managed by software. What is fundamental reason? Hardware cost is too big? Yeah, but more than that. There are fundamental reasons. Okay, no, abstraction in terms of level of interaction, translating virtual to physical, file offset to physical location. They're same, right? So you can implement it hardware. Similarly, like PageTab. Obviously, implementing software is cheaper, but is there any fundamental reason that file system designers does not ask the CPU to building this indection? Cause it's logical address? No. Why? So this is DRAM. This is SSD and HDD. What are fundamental difference between the two? What are first fundamental? Flexibility? No. Speed, exactly. Slow. They are slow. Okay. So, even if this trap also happens in the software, it's okay because these devices are slow. These are microsecond to millisecond unit. These are nanosecond units. So it's impossible to implementing this mapping by software. It's not. However, this time granularity, like microsecond and millisecond, operating system can implement it and populate it and traverse it. Fine. Okay. So when virtual address is accessed, then MMU translated. When file accessed, operating system, file system travels it and get the location of each code because this speed. In the future, if these devices are getting faster and faster, then this index implementation may change it to hardware. But today, the storage speed is not that fast as DRAM, so software implementation is fine. Consequently, this implementation is pretty flexible and software. So this is file offset, and this is a disk block, and any function which can map offset to block. Okay, this is a level of injection. There are many different indexing schemes are invented. Tree is fine, but is there any kind of good function, good indexing scheme that mapping this big, large file offset space to disk block? We learn, indexed, contiguous index, FAT, index allocation, and extent. Any other data structure you can bring up? Any other data structure? What other data structure you can think about? Linked list, tree, and hash table. Okay, some file system using hash table to index location. Okay, so there are like tons of index. As far as I know, I studied this index, collection of index, what index performs well, radix tree, and the other trees, and they are different pros and cons. Most interesting way, we learn some algorithm, some techniques where I don't know the relationship, but this some kind of access sequence, and this is block access sequence. By looking at this input and output, we can actually building intermediate relation. This is kind of pretty, how can I say, downgrade of the benefit of this algorithm, this technique. But what techniques actually kind of providing this guarantee? Input, output, identify a relationship. What? You guys popular, right? You don't know the internal kind of things. You can actually kind of giving the input, giving the output, you can observe exactly. Learn the index. So using some machine learning algorithm, some light machine learning algorithm, usually kind of some non-linear or simple linear or combination of linear regression or MLP, computer architecture operating system generates building the index, which having a much lightweight and fast translation between large file space into this Kubla, which is called learned index. So these are kind of burgeoning, kind of diverse area to identify, building new data structure for that. Okay, so that's kind of, you have to keep in mind. In the future, people may using, index based on the MLP. Yeah, so there are some research comes out to building index for this. And MLP is accelerated by hardware. So Professor Jong-se Park and I actually proposed the idea, and Jong-se Park actually building this index and using MLP-based indexing and then accelerate this index operation using the FPGA. Yes, that'll be the idea, right? Okay, so keep, when you are looking at this thing, if you can just kind of memorize this indexing, oh, indexing is this one. But if you look at this indexing structure like this design problem, okay, you can use different way of thinking. They use ML for creating the mapping scheme. Can it guarantee correctness? It's interesting. No. So in London index, it can actually kind of probability of this range. So we have to kind of linear search within this kind of probability guarantee. So this indexing guarantee some location here. This is not exact location. Within probability, with good probability, there are some blocks. And then you have to kind of small range of linear search to exactly find the correct block. That was the idea. What good point. You know that. So yes, it's not 100% correct. So you have to do some kind of exact matching at the end. So some data structure to perform the exact match, but guarantee that more than 60% to get guarantee that some location within some range, and you can do it. You can do linear search, simple linear search for the range. All right, so that's the learned index scheme. Okay, so likewise, this indexing is implemented software. So there are many ways to thinking different data structure, concurrent data structure, and other stuff. It's a popular area for in file system research. All right, so that's all is index, and let's move into directory. So like a directory is also having this a block, special file that contains file name and inode number. So how to organize this directory block from directory inode. From directory inode, you have to locate directory block. Okay, so there's several ways to build this from directory inode to directory block. One way is using the existing indexing scheme. The other way is different data structure. Table. So there are some kind of special tables for directory. So there's some kind of special data structure like a tree, internally table, tree, and some hash table from file name to inode block. So this table implementation is popular for 3. And from directory inode to directory block, we're using the file indexing. Through the file indexing, reading a directory inode, through the file indexing, locate file directory block. Within a directory block, there are several kind of organization to map this file name to inode number. One way is table, tree, hash. Okay, so this simple system using this table of linear list, which directory looks like this one. So each one first, there's some kind of four bytes inode number and size of length and name length, and here dot, and this is our dot foo bar, which has inode number of this each. Okay, by searching this directory, so these are directory block. by searching directory block, you can scan string compare. So I want to finding foo, then string compare and directory returns inode number 12. Okay. So for this one, I explained that, for directory, starting directory walking from root and directory, right? So in the design section, design part, I explained how directory walk, so what kind of searching operation happens to eventually locate this directory block, for example. So how to locate node inode number dir? So you have to search in the root directory. So root directory inode number is specified. For example, inode number 1, always pointing to /root and root leading inode number. You can look at the directory block for root, and here /dir and inode number. Find it. Okay, directory walking. This when directory is organized, this in your list. Okay, so that's the basic stuff about implementation detail. Let's put it all together to understand what happens when application issuing this read and write system. So review that this is kind of a read path where when you are trying to read it, it first search memory. If it's there, then this is page cache. So file system searching the page cache, and if there's entry, and return. If not, then reading data into cache and return. Okay, that's the kind of common read path. Here are examples of reading a file. First, you first open one, read 3 blocks, that operation. And here are on disk layout. Okay, follow me. This is kind of most comprehensive view. So you have to understand all the details about this one. So there are data and inode bitmap. No inode allocated, no data blocks allocated, so no operation happens here. Okay. First, when you travels open this file, you have to read inode for root first. Okay. Then looking at the inode and searching for directory of root directory block and identify inode number of foo. Okay. And then read foo inode. Okay, where is it? From a root directory block. Okay. Looking at root inode, you can locate root directory block and then searching the root directory block to figure it out foo inode number and read foo inode. Okay, then you want to read 3 blocks, right? Then for this one, this root data, exactly root directory block, read it, and after reading a foo, and you have to read foo directory block. Read it. And then you are finally can read bar inode. Okay, so these are sequence. These are sequence. Are you guys following? Okay, so there's a block. And then with 3 blocks, subsequent 3 read operation here. So for read, first you have to reading a block. So at first you have to read bar inode. Okay, and then read the first block. From the read bar inode, you can locate it, the first data block, which is 4 kilobyte. Okay, read it. Then write inode. Okay, why it happened? Recall, this is inode. What is the write? You just read it, but write operation happens underneath. Why? offset. You just kind of reading and finding location. Okay, what? Modification time, do you modify? No, what? Access time is modified. Okay, access time is updated. So you have to write back. So due to access time, you have to write back data. Okay. Then the second read, access time call goes to kernel, and kernel read inode. Okay, and read data blocks, and likewise write data for access time. Okay, so that's thing, but this operation read and repeatedly read bar block for every read operation. Let's say this disk read from disk. This read operation actually happened to disk. Second read operation of bar inode. Is it from disk? What do you think? So discrete. No, actually. So to improve performance, inode cached. So specific inode cache. So inode is never prefetched, but inode itself is cached. And first time it read from disk, and second time not 100%, but it may read them from the DRAM. So it's more likely to from inode cache. Like page, like directory, like this page cache, there is inode cache, where the inode blocks are caching into inode cache. Okay, beware of that. So subsequent read of same inode may served from the inode cache. Not 100% guaranteed. These cache blocks can be evicted, but more likely that happen. Couldn't we update access time after reading all three blocks? Chanyak, good, yeah, right? This is kind of looks stupid, right? So why do you need to update access time every time, So yes, good point. So Linux supports relative access time. So yes, so current operating system having every time when you access it is really slow. So they support different also well. The file system providing some optimization where relative access time. Sorry, where why doesn't school just go? Sorry, it doesn't have not good no good material for that. So, but let's see. So yes, because of that, file system has special option called rel A time. So every time you are updated the A time, every time you read the inode, so if you can do this option for rel or access time, it does not update access time. So access time is work like modification time. When you actually write, the access time is modified. You have some option for that. That's kind of a bummer for read speed. So Linux by default disable the access time update every read operation. It does not in practice, but Yeah, that's optional. So, but correctness for correct file system implementation, you should do write inode back to disk. That's inconvenient, but that's for correctness, right? Access time is important. Why? Let's discuss a bit more. Why access time is important? You have to, as an administrator, you have to scan through how frequently files are accessed. So this collect statistics to understand files statistics. The correct updating of access time is important in some file system. So it's at the cost of this write operation. It has some Linux, the file system write data on every access, on every read. Right? So that's it. But this is kind of basic stuff, so I have to stick to the original design stuff. But there's an option for avoiding this write operation. Does it make sense? In practice. Okay. All right. Second, a bit more complicated. Write IO path. So write path in the write, every time you writing a data, first the blocks has to be written loading into cache. One exception is that when you're writing 4 kilobyte, you don't need to because the size is overrated. But if you can write the data less than 4 kilobyte, you have to read blocks and update some portion and write back. You call this read, modify, update. Okay, because basic units for writing a disk, writing a data is 4 kilobyte chunk. If you can update blocks less than one blocks, and you have to read it and modify right back. So that was the basic rationale for write, and so that purpose blocks are cached into the page of. So that's right. So let's take a look at this example. So this example is creation and writing three blocks to operation. So this is the creation. This is the subsequent 3 write operation. For creation, first you have to locate it full directory. So read root inode and read root directory block and read full inode full and read full directory block. Then what is it? Then inode bitmap read and write. What? Why? What inode? Talking about here. What inode? Inode for who? Whom? For not slash r. Okay. So you have to create this one. So this is a newly created file. So reading and updating the bitmap for bar. Okay. Let's say you are allocating the inode bar. Then the first thing is that, let's say bar inode are decided full. Then first bitmap update. Then you have to allocate inode, which is this one. Okay, so those of who are forget about that. So to allocate bar, first you want to update inode bitmap, and then start using the inode bar, for example. So 2 blocks are really actual inode and bitmap, which are providing allocation information for the bar inode. So update inode bitmap first, and then actual inode. That comes to this. That comes to this inode operation. Okay, then full inode, right? What is it? Why Why foo inode has to be right back? Whose inode? Why does the foo inode has to return back? No, these are inode, right? These are inode. Sorry. Why foo inode is written back? Size, okay. Good. So say this is your full block, and you are adding new bar at the end of table. Then what changes? Obviously, access time and also size changes. Size may increase. So I notice return back. Okay, and this foo. So you are originally this is for foo, and then you are dot, and you are adding slash bar here, and because of that, the size can be changed. So you have to return back. And this write operation, talking about new entry are added in the foo. So foo data block. This is, for example, foo directory block has to be written here. Okay, follow sequence. So to create this one, first read root inode block again, and read root directory block, and read foo directory block, and read foo data block, and update inode bitmap, okay, and write back this foo data, and write back this foo inode, and update foo bar inode and foo inode. If this sequence changes, writing foo bar inode first and foo data later, does it work? Does it work? Okay or not? Incorrect? Correct. This is example, right? Okay. So later we talking about some file ordering operation in crash consistency, but it's fine. You can create bar inode, write bar inode first and updating data blocks later. Fine. Okay. Eventually, after that, you can reorder this operation. But in next lecture, we will discuss the implication of this reorder operation. But for now, it's okay. You can change it. But you can correctly, what you want to do is that you want to write this persist this foo blocks and persist this bar inode block. What you have to do. Okay, so that's creation. After that, the write operation. So for write operation, first to locate directory block, look the data blocks of bar, you have to read inode and locate it, located bar data. But bar is first created, or you have to newly allocate blocks, which cause this data block bitmap. Data block bitmap is block data blocks are allocated or not allocated. So file system allocate new data, which cause this read and write data bitmap, and eventually write bar data bitmap. Okay, then you have to write back to bar inode. Why? Access time, obviously. Plus, what are changed? What inode information is changed? Size. And one more thing. And modification time. Okay, access time and modification time and size and what? What? Length, size. What? Okay. New data blocks allocated 0 to 100. Okay, so data blocks, direct blocks. updated. Access time, modification time, size, and direct block information are changed. So update inode. Okay, someone asked the question, why is the read operation of bar inode needed before write? Oh, so again, same thing. So you want to write data, then the writing of data may require for modifying the itinerary states, right? For example, access time, modification time size, and directory. So you have to read it and need to update it bar inode. So read operation require. They may cache, but read operation require. Can update, does it make sense? Can you update full inode first before writing full data? And when creating full wire, yes, you can. You can do it. So that's okay. But for yes, for now, yes. Let's talk about crash consistency later. So the ordering, the meaning implication ordering, we will learn much later. But for now, it's okay. Any questions? So we have to update inode. So read bar inode first and update it and write back inode into storage location. I think the mean read and write bar inodes during create. Oh, sorry. Did I misunderstand? Read and write bar inode during create. Oh, this one? I'm talking about this one, bar inode. Sorry, oh, it's complicated. Is it okay to erase this one? So there are many, informations that. So are you asking this and this information? Sorry, if you can confuse of this one, I will get back to you after, you can ask question after finishing this lecture. So, okay, let's get back to why do you need read and write operation. Who inode write and who inode write and who bar write, who data write, who inode write, who inode write, and who data write. Who inode write, who data write. They also can be changed. Yes. It's okay. So this operation, write operation can be changed after and during the creation of during the creation. It can be changed. All right. So that's the write operation. Likewise, when you are writing a second block, 3 blocks, so adding new blocks in the file, 1 block, and adding 1 more block, 4 kilobyte block. So you have to allocate bitmap and read and update the new allocation and write data and write persist update of information. So that's append operation. But if you are update, for example, I don't want to adding new file, so I want to kind of update. Is this data bitmap operation happens or not? You can update it. This bitmap read write operation happen or not? No, right? Because this is file. So no newly allocate block created. So in case updates, bitmap read write operation does not happen. Okay, so yeah. These are things. Okay. This operation is really complicated, and textbook actually providing good kind of simple explanation, but you have to think about where why this read and write operation and why bitmap write operation is necessary, looking at the on disk layout and figure out that. So these are very details at the end you need to understand. I think it's this thing is maybe complicated without understanding the on disk layout, but take a time to understand this read write operation sequence. If you have any questions, feel free to ask in the Piazza. All right, so that is the detail of read write, and that is kind of key. We discussed key contents of file system implementation. So I explained that file systems are about detail. So can you understand what I'm talking about? What my intention to, file system, understanding file systems require you need to understand very detailed file system to understand the behavior of these file operations. So these are actually kind of implementing the file system in Linux. So file system is super complicated code. All right, so that's all. And let's moving to next topic. Best file system. Okay, so by the way, so this Wednesday we have interview for undergrad, newly, for the school-wise interview day. So we don't have class, so no class in this Wednesday. And last time, so next Monday we discuss the festival system, let's talk festival system and crash consistency. That actually kind of end up this course of the semester. Okay, so no class this Wednesday because it's kind of an official holiday for school for interviewing, the applicants, undergraduate applicants. Okay, all right, let's begin. So we know the basic background of file system, and this fast file system is new file system. It's improving original file system. So original file system is developed by this guy Ken Thompson, and where it using Superblock, and there's inode RIST and data blocks. This is our own disk layer of that. So Superblock has information on basic stuff of file system and head of the free list. So linked based location of inode and data blocks. And this inode RIST is referenced by the inode RIST. So inode has this linked location of inode. And data blocks belongs to any file. So these are original file system 1970. So it will used. However, people identify that this original Unix file system is slow. So there are three reasons reported. First, the block size is too small. So Unix using the 512 bytes. So 512 byte blocks are too small. So at the earlier days, hard disk is really expensive. So if you can increase block size to 496 kilobyte, what was the problem? Why they don't use small? Why they stick to using the small blocks? Why they don't use increasing the block size? Internal fragmentation. So hard disk is really expensive. So internal fragmentation, space waste is expensive at that time. Today it's fine, right? Hard disk cheap, but at this point, really expensive. So they stick to using the small blocks because file index space available for file index is too large. Okay. We'll get back to this. We will discuss these questions one by one. Second, using the free disk is really bad. So managing allocating contiguous block is very hassle using this free disk. We know the answer, right? Eventually you use a bitmap, but at this point, file system is implementing this free list based allocation. What's problem? And third problem is well-known poor locality. So these are inode and data blocks are located far, so it causes locality problem. We will closely look at these three problems. Okay, so before going to that, I want to introduce these important things in the systems research. So to handle this problem, to address this problem, new file systems invented called fast file system, FFS. FFS is modern prototype of file system. Linux and Windows, all this modern file system is actually kind of follow the principle provided FFS. So it's kind of very earlier initial seminal work for defining what is the efficient file system. But what I want to point out is that, the approach. So here, discussing this FFS, it kind of shows that, how systems research, let's say they were system A. And you find that systems A is inefficient. And you want to improve system to B. I want to improve it. Okay, how to? Okay, so they're working original Unix file system, and there's a new, I want to kind of invent a new file system. How to identify this inefficiency of original file system? What? Measure. So you have to profile, understand the performance every step. For example, you can actually kind of measure the inode speed, inode access speed, or disk layout, disk bandwidth speed. You measure the state of our system. And identify, understand fundamental problem. So, it seems like an original file system has this design principle. I think this design principle is invalid nowadays. I think this design principle wrong, inefficient. Wrong is strong word, sorry. Inefficient. So because of this observation, you observe it and get an idea to build better system to address these inefficiencies. That is how typical systems research. Observe it, measure, and enumerate inefficiencies and defeat it by new design. Okay, so FFS typical follow this formula to improving file systems. So I want kind of, this is good example for how systems research work. So design a new file system structure and allocation policy. The key idea for FFS is what? Disk aware. The file system is, some file system is implemented, so for support some POSIX APIs, but to providing maximum speed, file system has to understand some semantic of disk for locality. So that's key idea. Okay, I think this inefficiencies comes from the disk unawareness. I want to redefine pre-design file system, make disk aware. So to measure, look at the file system operation design. And what? These are the observations. From the measurement, FFS guys identify these three problems. Problem 1, problem 2, problem 3. Okay, meaning that each problems has to be backed by some experiment. I want to run some experiment where block size is small. What are consequences? You evaluate it and report number, and people believe it. Okay, yes, because of that, this system has kind of low disk bandwidth. Okay, this is problem. Okay, I got it. And from that, you have to prove it. Prove by giving quantitative result. And then you redesign of FFS. Then you have to prove it. Your design works well. How to prove it? Okay, FFS, you learn observation, you learn several experiments, observe the problems, and prove by some kind of quantitative, experiment. And then from that, you have some idea. This is idea, right? This is your thought. Maybe wrong. You have to prove it. How to? How to prove that your design idea is correct? Measure again? No. To measure, what do you have to do? Implement. Okay. It seems like my design, my thought seems okay. So you have to actually implement it and run evaluation, run measurement again, and shows better performance. So these steps are systems research. Okay, because of this step, we are experimental scientist. Okay, so we are not like theoretical scientists. So in systems research, building idea. This is your thought, unclaimed your thought. So unproved your claim. So you have to prove it by implement, evaluation, showing better performance. So these steps are typically what experimental scientist does. Okay, so this FFS exactly following this cycle of systems research. Let's take a look. So FFS scientists Unix file system is slow. So the folks McKusick and Joy, Leffler, and Flaby, this is really the kind of guru file system guys in the 80s and finding out how to implement file system. Basic idea. Key idea is discover this. Let's take a look. First problem. Block size is too small. To show that, we need to show this inefficiency of blocks too small. Block size blocks too small. So they measurement. Learn this measurement. It's simple. So let's say by increasing size of block, or these are size of original block size of original Unix FS, and increasing the size number of blocks, size of blocks. So they measure two metrics. One is space wasted due to internal fragmentation. One is your bandwidth, so disk performance. It turns out that this is a maximum device bandwidth, but when you are using the 512 byte blocks, it turns out that actual application only can utilize 2% of maximum disk bandwidth. This is absurd. These are wasted performance. Device speed, your actual speed, huge gap problem. Okay. Clearly, by increasing number of block size, the performance can grow up. Okay, can grow up. So block size increase, bandwidth, but you have to deal with. Okay, so large block size is good. Okay, but to use a large block size, you have to the space waste problem. Again, space size. You have to kind of address this problem. Again, what? Internal fragmentation. Again, so what's the idea? But the idea is you already learned from the malloc. What is the idea? Growth? Yeah, growth similar, but in malloc, what's the strategy? When you allocate mmap to the Linux 4 kilobyte, and what to do? When application try to allocate object, lazy loading, when you allocate 4 kilobyte chunk from the file. So let's say page size is 4 kilobyte, but object size is 128 bytes. Then what you do? What's the idea? Malloc, multiple mallocs. What do you have to do? Each malloc, do you allocate new page blocks? For each malloc operation, do you call every 4 kilobyte chunk? Again, malloc 128 bytes. And then subsequent malloc 256 bytes. What you do? So this malloc allocate 4 kilobyte. This malloc allocate 4 kilobyte. Do you? No, right? Split it up. So you can actually speed up mallocs different object idea. Right? You did it. Same thing. Which is called fragments. So the file system having a large block, 4 kilobyte and 892 byte blocks, 4K block or 8K block, and these are chopped into small allocation unit called fragment. This collocation happens by this large block. So indexing unit, but actual allocation unit smaller fragments. So this fragment size is specified at the time the file system is created. So limited one block having 2 fragment, 4 fragment, or 8 fragment, depending on the configuration. So this one providing much higher speed for large files, large blocks, and reducing the space for small files and endo files. So let's take a look at how fragment works. Let's say this is file size with 4 kilobyte. This is file size is 2 kilobyte. And let's say block size is 4 kilobyte and fragment size is 1 kilobyte. So on 4 kilobyte, without using the fragment, it will allocate entire text of 1 kilobyte, 4 kilobyte chunk, and 1 kilobyte only use. This is wasted without using fragment. But with the fragment, these blocks are splitted with different file. B, A. So these are fragment. Okay, so, and then this 2 kilobyte, previously it used this 2 kilobyte file takes a 4 kilobyte chunk, but now are shared these 2 files. And then when you append the 1 kilobyte to this blue file, then allocate new fragments and create mapping. Okay, and then let's say append one more file, 1 more kilobyte to blue file, then create new blocks and chunk. Create new block and allocate this 1 fragment. Allocate 1 more chunk, 1 more fragment, then say 1, 2, 3 kilobyte is used. So these are 4 kilobyte chunk are newly allocated, and they are migrated into this one, and then freed. So because of that, this managing and actual allocation and managing units are different. Indexing management, the indexing unit and allocation unit are different, so that this small allocation happens to shares 1 block shares between the files with a small fragment. Once fragment, this file size grow up to takes a 1 block and then migrate it. So using this scheme, it mitigate internal fragmentation when using large blocks. That's the idea of fast file system. Similar, not exactly same, but similar stuff we learned from the Malloc implementation. And then the next 2 problem is unorganized free list and bitmap and pro locality. So, but time's up. So let me stop here. And let's continue to talk about the FFS idea to improving original FS, problem 2 and 3. We'll discuss the rest of stuff in next Monday. Okay, so that's all for today. And if you have any questions, feel free to ask. Any questions? How do fragments allow high transport rate speed for large files? So when you are using the large files, for example, the file size is 16.4 kilobyte, then you are using the 4 kilobyte blocks. But if you are using the small blocks, 512, when you're reading the 16 kilobyte, you have to read index and locate 512 bytes. Locate 512 bytes, much slower. So like a similar effect of extent, using extent. Using a large blocks in large files, you can locate it, these large blocks with a few index, so providing much better performance than using small block size. Can you explain one more time about when updating access time is important? Okay. So, access time is used. Say administrator to find files modified or accessed, for example, 2023 to you want to find it because at this point there are some kind of incidents happen. Someone actually kind of accidentally reading a file. Someone attacker comes to the system and they read the file. So I want to kind of what files actually read by attacker. So then administrator actually kind of scan query this command where which files are modified, which files are accessed between this time period. So access time is important. Correctly updating the access time is important for this administrative operation. Does it make sense? Okay. Why does reducing the number of index searching makes extends faster? Isn't it? Cache and very fast. Yes. So index are cached, but you have to search. So to locate block, you have to search one index, locate a physical location, locate another 4 kilobyte index search, or locate 5 block operation. So if index search happens once, then reducing the number of index lookup operation, data structure lookup operation is reduced, so it can provide a better performance. Yeah, they are cached, but in case of lookup operate, so reduce the number of lookup. It's one thing. And these are a bit details I didn't explain, but here's actually kind of why speed up happens internally in the large blocks. So say when you are reading 4 kilobyte, or using 16 kilobyte. To read, you have to DMA. For this one DMA. So large reading one chunk, you have to issue only one DMA operation, which is much faster throughput. That's called a caveat. Actually, it reduces the number of DMA operation to stick operation, making much faster. This intent, but there's actually kind of a thing. Reason that the reading large chunk of blocks are much faster because ISO system. So does it make sense? Okay. Is it more about continually rather than lookup? Yes, it's about So in small chunk, you have to look up the index and perform one DMA. Look up the index, one perform DMA. But in case of one extent, this is a contiguous chunk, then you can make a one lookup and one DMA operation. So it's combined. Lookup and contiguity are combined problem. And also in modern computer system provide a scatter gather DMA, whether blocks are spread out, you can perform the one DMA operation. So lookup is more related to this one DMA operation, actually. Does it make sense? Okay, can you explain what changes that file to operation? Okay, cool. Let's go to the file. 5. Oh. Next question. So what was the question? At inode create, writing. So what changes are writing to full index node? Full inode. This one, full. Okay. So you are creating bar, which means that this is full directory /full. And originally there was dot current directory, dot parent directory, and you are adding bar. So it was length X. Now you are increasing X to Y. So size increase. And modification time and access time are updated. Sian, does it make sense? These are two information. Does it make sense? Okay, and I can. Why read operation of inode bar needed before write? Bar inode. This one, right? Okay, so for that one, bar, good. So yeah, here still. This inode. All right. And bar inode, when you're creating a bar, so if you look at the bar here, you have to set up several kind of permissions and who is owner, you need to modify it. Okay. So when bar first created, these field has to be modified. So bar inode has to be read and updated on creation. Is it your question? What kind of things can change it? Yes, because it's ownership and permissions stuff actually can update it on creation. So you have to read it, modify it, and write bar inode. Does it make sense? Do we need to read all previous data? All previous data. All previous data. So specifically, this is what happened. So look at its inode has 4 kilobyte blocks. There are several different inode. Here, inode bar. And you can read the entire block. And here are by inode part, and you modify and write back. Do you need to read the previous data? Now, no, but inode, likewise, you cannot read by inode only. You have to read the entire this block. Okay, and modify by inode or write back. Because inode size is 128 bytes actually. Does it make sense? So read operation, read operation can start from cache, but at this point we have to assume that this blocks read and you have to modify. So you cannot blindly write this data without reading entire 4 kilobyte block in disk. For reading page file 37, are writes for modifying last access time? Yes. Or write? Yes. Write also modifying the last access time? Yes. Write both access time and the modified. Yeah. Yes. Any other questions? Okay. Yes. Okay. So if so, why don't you have write the directory inode to modify their access time? Why don't you have a write for directory inode to modify the access time? Where is it? Foo, right. Bar. Oh, so you are talking about this. Oh, so this right? So why no write happen? Is it your question? Is it your question? Bar directory update bar inode. Bar directory write update bar inode. Why isn't the write for full inode to modify access time like write full inode? In which case write full inode happens here? Here? I think I don't. Are you asking the question here in read path and write path? Which path are you talking about? Read. So there is no full write operation here. Why full write operation happens here? Full inode never written here. Write inode, this modification time happens by data write. Okay, not inode write. So there's no write operation in full var data. So full inodes never, full inodes access times never modified because there's no full data write happen. Only read, right? Oh, you are talking about here, right? Because full data is read. So full data access time. So likewise, there should be write operation here, right? Is it your question? Oh, I see. Yeah, technically you're right. It seems like full data is accessed for this one. So access time, because full inode is also accessed, write operations to be placed here. But I think I got this example from the text, but the textbook actually kind of eliminate this one. But in practice, putting the write operation here is correct. You're right. Good point. So, but I want I want to make a consistency with textbook, but yes, I think textbook miss this information. It should be written because full data is accessed at this point. Good. Any other questions? For this part, I will clarify. Any other questions? All right. So thank you and talk to you next Monday. Bye.